Hello everyone, my name is Perry from Rutgers University, and today I will be presenting our paper, Finding Berries, Segmentation and Counting of Cranberries Using Point Supervision and Shape Priors. This project was done in collaboration of Rutgers Electrical and Computer Engineering Computer Vision Lab, Plant Biology Department, and the P.E. Marucci Cranberry Research Center. So, to briefly go over the core problem and motivation. We look to find an affordable solution to cranberry yield and sun exposure estimation. Yield estimation is generally done by manual counting or estimation by weight, while sun exposure estimation depends on local weather reports, which is often incorrect and may lead to yield loss caused by heat stress, which cranberries are highly susceptible to. This work aims to count and segment cranberries from a non-invasive aerial view, capturing the number of cranberries exposed to the sun and their albedo levels. We minimize cost by using center points annotations, which are an order of magnitude cheaper than pixel-wise annotations. We collect only RGB imagery using off-the-shelf drone equipment. Since circular shapes are common in cranberry data, and agriculture in general, it was a natural direction to overcome the lack of spatial information lost by using center point supervision. Let's start with a short recap on terminology and background. Segmentation is a task of mapping pixels in a given image to specific labels. As you can see in the center image, all pixels that belong to the cranberry class have the same predicted pixel value. On the right is an example of instance segmentation, where different instances of the same class have different predicted pixel value to indicate different instances of cranberries. State-of-the-art typically requires an additional step in the form of a region proposal network for this task, which we eliminate in this work. Counting, as the name suggests, is the ability to compute the number of occurrences of a given class in an image. Perfect instance segmentation infers perfect counting. Our proposed method is called the SSS network, which is composed of three components: segmentation, split, and shape losses. Let's go into more details for each branch. First is the segmentation loss branch, which uses masks annotated by the set of positive and negative ground truth points, P sub P and P sub N, which live in Y, to guide the model predictions towards positive locations and away from negative locations. It takes a probability distribution of the predicted mask and penalizes low probabilities in positive points and high probabilities in negative points. Next, we have the split loss branch. Split loss serves two roles. The first role is to define where cranberry pixels may exist. We do that by using our selective watershed algorithm, which uses positive and negative ground truth points to generate more selective regions chosen as viable cranberry pixels. As mentioned before, Y has both negative and positive ground truth points. We can then use the classical watershed algorithm on Y to obtain the set of regions R. R can be separated into positive regions, noted as R sub P, which correspond to positive points, and negative regions, noted as R sub N, which correspond to negative points. You can see on the right the difference between the classical watershed and the selective watershed output. This dramatically narrows down pixels of interest for given cranberries. We then use those regions to ensure separability of cranberry instances by penalizing predictions outside of the set of positive regions. The last branch features the shape loss, which aims to better structuring of blobs. This work explores two shape priors that are known about cranberries: convexity and circularity. Here I will be presenting the intuition behind convexity loss. We know that a convexity measurement of a blob can be defined by the area of that blob divided by the area enclosed by its convex hull. If the blob is convex, C of B is simply 1 over 1. The less convex the blob is, the lower its convexity measurement. Once this measurement is obtained for all blobs in the predicted mask, we can regress over them and compute its Huber loss. Since we encourage convex measurement, our ground truth is always 1. Circularity loss follows the similar structure, with more specific details in the paper. To shortly summarize Triple-S network, during training procedure, we can say that the segmentation loss pushes towards the point, split loss pushes towards a region, and shape loss pushes towards certain structures. In practice, that requires some hyperparameter tuning to make sure that neither of the segmentation loss or the split loss overtake the other. The quantitative results show how our method does compared to other state-of-the-art point supervision counting and segmentation methods. We can see that circularity loss function provides the best balanced performance, expressed as Q sub CS, which is the ratio between counting and segmentation performances, while convexity loss provides the best segmentation results. For counting, we found that state-of-the-art methods have difficulties with our Cranberry dataset and do not perform as well. We also examined the contribution of a dedicated count loss for ablation study, which can also be found in the paper. Those are some visual examples predicted by our method. It can be seen that even difficult examples where colors and shapes are irregular, the model is able to correctly identify and separate overlapping cranberries. This work also introduces the largest repository of cranberry fields aerial imagery, containing more than 21,000 images. Images were collected weekly with a fixed drone trajectory to ensure same regions were captured at each collection session. Here are some statistics about the datasets. Images have an average of 32.22 cranberries per image, with a minimum count of 0 cranberries and a maximum count of 167 cranberries. Center point annotations took an average of 4.32 minutes per image, while pixel-wise annotations took an average of 22.13 minutes per image. Pixel-wise annotations have an average of 33.72% pixel cover. The dataset is available on the project website and on our GitHub page. That was me. Thank you for your time.